One of the greatest myths in digital audio is that, as we're going to look at upcoming slides, that they're shaped like staircases and then that much of the brittleness is a consequence of the steps. That is total nonsense, and that is not true. It's how we're representing it. But what is happening so fast behind the scenes with the samples, and an important thing, is the reconstruction filter. So on the D to A, this is then putting the samples back in order to create the analog signal. So with a well-recorded and proper equipment, the emergent analog signal is not only smooth, but virtually identical to the analog signal. And there's some video I will show you of that. So backing up a little bit, we have what we know as the Nyquist Theorem, and there's a couple different people involved with that. We call it the Nyquist and sometimes Nyquist Shannon, but Vladimir Kotelnikov was also working this simultaneously. So the three of them all come with this idea. And the Nyquist theory is the sample rate must be twice that of the highest frequency to be recorded. And we'll see some errors that come if you don't, if the Nyquist theory is not paid attention to. Again, at this point, it's a theory because they can't prove it because the equipment does not exist in the 30s. Based on the Nyquist theory, if 20,000 hertz or 20K is the highest frequency, what sample rate would it need to be? The answer is at least 40 kilohertz or 40 samples per second. So we know the principle of digital recording is based on two principles. Sample rate, that's the number of snapshots of the incoming voltage per second, and then our bit depth, which is the number of values assigned to the dynamic range. So if we look at our incoming analog signal, we have our frequency, which is going to be how fast we're doing the sample, and then our amplitude. We then get, again, these stair steps don't represent exactly what's happening, but it's for us to see as a representation of the analog signal. So the snapshots represent our incoming voltage. The sample rate is the amount of snapshots taken per second. The higher the sample rate, the more accurate. So we look through here and we have increasing sample rates. So very poor sample rates to higher sample rate, and we get closer and closer to looking exactly like the incoming signal. A lot of us still revert to the sample rate and bit depth of CDs because that's what most files end up in their final 2-track format. So understanding this, while CDs don't exist, we use this as our standard. And the sample rate of a CD is 44.1 kilohertz. And again, that's the computer taking a snapshot of the voltage 44,100 times per second. Standard sampling rates that you'll see, we've talked about CDs at 44.1, which means the highest frequency it's able to accurately produce is 22,050 hertz or 22.05 kilohertz. DVDs and DATs, digital audio tape, are normally sampled at 48. And other sample rates you'll see are 88.2, notice that's just a doubling of 44.1, 96, a doubling at 48, and even all the way up to 192, and in fact we're going beyond that. Bit depth is in relation to our dynamic range. This is the level of amplitude. So these are our steps across or below the line in relation to our frequency. So the more amplitude levels that we have, the more accurately we record the dynamic range. In terms of bit depth, if we have a word that's 4-bit long, we have 16 possible values. You can see we have either a 1 or a 0 for each of the slots. So all zeros would be one value, all ones would be a second value, and then the 1001 is a third value. If we have an 8-bit word length, we have 256 possible values, and it looks something like this. 8 slots where you either have a 1 or a 0, and this is in terms of amplitude. If we have 16, now we're in CD quality. We have 65,000 possible values, and if we go to 24-bit, which is generally where you'll start your projects, you have over 16 million possible values. So there is an incredible bang for the buck going from 16 to a 24-bit project in terms of dynamic range. And you can see here, with a smaller bit depth, we have a noise floor and our signal are much closer to each other because we still have to leave some digital headroom so we don't have clipping. But as we increase the bit depths, we get farther away from our noise floor, noise that's inherent in the microphone preamp, cable, RF picked up by the cable, and things like that. We can leave still an incredible amount of headroom, but we have greater dynamic range, we have a higher signal to noise ratio, and we can still leave that nice headroom at the top. So there's a lot of bang for the buck recording at larger bit depths, even though it's going to end up on Spotify.
Okay, it's go time. We begin by converting an analog signal to digital, and then right back to analog again with no other steps. The signal generator is set to produce a 1 kilohertz sine wave, just like before. We can see our analog sine wave on our input side oscilloscope. We digitize our signal to 16-bit PCM at 44.1 kilohertz, same as on a CD. The spectrum of the digitized signal matches what we saw earlier and what we see now on the analog spectrum analyzer, aside from its high impedance input being just a smidge noisier. For now, the waveform display shows our digitized sine wave as a stair-step pattern, one step for each sample. And when we look at the output signal that's been converted from digital back to analog, we see it's exactly like the original sine wave. No stair steps. Okay, 1 kilohertz is still a fairly low frequency. Maybe the stair steps are just hard to see, or they're being smoothed away. Fair enough. Let's choose a higher frequency, something close to Nyquist, say 15 kilohertz. Now the sine wave is represented by less than 3 samples per cycle, and the digital waveform looks pretty awful. Well, looks can be deceiving. The analog output is still a perfect sine wave, exactly like the original. Let's keep going up. Let's see if I can do this without blocking any cameras. 16 kilohertz. 17 kilohertz. 18 kilohertz. 19 kilohertz. 20 kilohertz. Welcome to the upper limits of human hearing. The output waveform is still perfect. No jagged edges, no drop-off, no stair steps. So, where'd the stair steps go? Don't answer, it's a trick question. They were never there. Drawing a digital waveform as a stair step was wrong to begin with. Why? A stair step is a continuous time function. It's jagged and it's piecewise, but it has a defined value at every point in time. A sampled signal is entirely different. It's discrete time. It's only got a value right at each instantaneous sample point, and it's undefined. There is no value at all everywhere in between. A discrete time signal is properly drawn as a lollipop graph.